Sounds good.
For the second Zoom talk of the conference, we have Sanath Devalapurkar, who's going to tell us about the geometric Langlands duality with generalized coefficients.
Yeah, thank you very much. I'm really sad I couldn't make it to this conference. There's so many people who, I don't know, I've only emailed with or Zoomed with, and I don't know, it would have been a nice opportunity to meet people. Also a lot of fun people to talk to, so maybe next time. Uh, okay, so yeah, I'm going to talk about geometric language duality with generalized coefficients. I recently changed affiliation, so I'm ex-Harvard now. Uh, okay, so here's a brief outline. I'll describe some motivation, uh, and then we'll do some basic combinatorics for tori to see what does geometric language duality say in this case. And then we'll describe I'll give a conjectural description of how language duality interacts with things like complex K-theory and elliptic cohomology and even the sphere spectrum. Um, and then in the end, I hope to get to a really interesting topic of deformation quantization. Okay, so what is geometric language duality? So in number theory, uh, well, there's arithmetic language duality, which relates to something like automorphic forms with representations of the Galois group and so on. But there's this analogy between number fields and function fields, and those in turn to three manifolds and two manifolds and so on. And using this analogy, Valentin and Drinfeld propose a geometric version of one. Basically, every time you see a number ring like Z, you replace it by a Riemann. And so in this geometric variant, the topology of the split reductive group, the topology of a split reductive group, uh, something like say GLN, is related to the algebraic geometry of a different group called the Langlands dual group. And we'll see how the Langlands dual group shows up in the case of a torus very explicitly in it, later. So an example to keep in mind is you have something like SLN, and then this dual group is going to be PGLN. So just GLN mod the diagonal. And so here's what their conjecture says, very roughly speaking. He says you take a Riemann surface and you pick some commutative ring K. Then you can look at the category of sheaves of K vector spaces in K module on the stack of algebraic D bundles on the curve. And the idea is that that should be related. So this is some topological thing, like something topological about this moduli stack. And the idea is that this category of sheaves should be related to the algebraic geometry of a different stack called the stack of local systems. But it's the stack of local systems for a different group, this Langlands dual group. Maybe one thing I'll say is that this Langlands dual group it's an algebraic group and it should be thought of as living over the commutative ring K. We'll explain this all in a second. I'm just trying to motivate this. And okay, this conjecture, as I stated, is not quite correct. It is sort of up this flavor that sheaves on the stack of G bundles should be something like quasi-coherent sheaves in the stack of local systems, but there's sort of deeper arithmetic phenomena that suggest that this should be replaced by something like INDCO. Um, okay, I'm not going to really get into that. So this is a very, very interesting conjecture, and it's generated quite a lot of deep and beautiful mathematics. And well, I want to discuss how you would try to understand this, especially when you eventually start to let this K be sort of a more general homogeneous. So one way to think about this conjecture is to try to approach it locally. So instead of thinking about G bundles on a Riemann surface, let's just think about G bundles on like a bubble. So that's like you have a disk, you have another disk, and you glue it everywhere except for at the origin. So it kind of looks like a little blip. This is what this bubble looks like. So D is a formal disk, and D surface is a function disk. So then you can still form this moduli stack of G bundles on the bubble, and this will look like basically you take the loop group. So this G of F should be thought of as a loop group. Uh, so that comes from G bundles on this function disk. And then you're modding out by G bundles on the disk itself. I mean, this is just like the same, like trying to write down a G bundle on the bubble through clutching functions. This is essentially what this identification is. So this can be thought of as like the quotient of G of F mod G of O by this G of O acting on the left. And this quotient, or maybe if you want G of F mod G of O with G of O acting on the right, But this quotient G of F mod G of O is a very, very interesting object. And there's this book by Presley and Siegel on loop groups where this kind of thing is studied in detail. It's called the affine Grassmannian, and it's denoted by GERG. It's some kind of loop group version of the psi protocol. And in this case, this geometric Langlands conjecture that I mentioned in the previous slide, it's a theorem of Bezer-Koplikov and Finkelberg when your coefficients are the rational. And so what does the theorem say? So if you apply some causal duality stuff, then the theorem just says the following. If you take the category of sheaves on this G mod G of O, so remember this guy is just G bundles in the bubble with coefficients in the rational numbers, then that's just a stack of that's just quasi-coherent sheaves on some stack, and the stack is just you take the coadjoint representation of this dual group. So this is some algebraic group, and you can take its Lie algebra and therefore its dual. You put it in some homological degree. It's just a vector space. So you just shift it, and you take the stack quotient by the coadjoint. So maybe ignore this like shift by two for the moment. Just think of it as like you take the coadjoint representation and you take the stack quotient by the group itself. So this is called the derived geometric Satake equivalence. And one could think of it essentially as geometric Langlands for P1. Just because, I mean, I told you that this bubble thing is sort of supposed to look like you take a disk and you glue it over the disk minus a point with the disk. And that's kind of exactly how you think of, let's say, S2 as, you know, a disk union a disk over a circle. So this bubble is some algebraic version of S2. It's not quite P1, but it's close enough that this equivalence gives you the geometric Langlands conjecture for P1. Um, so the question that I want to understand essentially is what happens when you replace this Q by other, well, commutative rings or commutative ring spectra. So I'm going to make some simplifying assumptions. So I'll assume that G is simply laced. If you know what that means, you know what it means. And it's also simply connected. So what this condition basically means is that your group is something like, say, SLN, or it's one of the even spin groups, or it's one of these exceptional type E groups. So in that case, this dual group is something very explicit. It's just you take the original group. So it has a center. For example, SLN has a center, which is the nth root of unity, and you just take the quotient. So for example, for SLN, G check is SLN modulo the diagonal matrices, and this is just PGLN. So that's the example that I gave. And in this particular case, this funny coadjoint representation for the dual side is just it's just the Lie algebra of G itself. There's no checks or no duality, nothing. And just rewriting the result from the last slide, you find that sheaves on G not G of O is quasi-coherent sheaves on a certain stack, which is just you take the Lie algebra of G and you mod out by the adjoint action of the group G on this Lie algebra. So for example, for GLN, for SLN, I'm just saying you take SLN mod G of mod SLN of O, and on this side you'll just get SLN mod PTLN, like the Lie algebra SLN mod PTLN. So one of the reasons this is very interesting, well, okay, so the many reasons it's very interesting. One is that it's actually a Fourier transform. So this G, I'll explain in a second, it's quite a huge space. And in this huge space, there's a particular, well, there's the base point, and you can therefore consider the delta sheaf at that base point. And this is a Fourier transform, so what it does is it sends things like skyscraper sheaves to objects which are supported everywhere. So this delta sheaf goes to the structure sheaf here. Okay, so what do we do with this? Well, one thing we can do is compute endomorphism. So if you compute endomorphisms of the delta sheaf, then you will just get cochains on BG. Just because, it's like sheaves on point mod G of O, and you're just taking endomorphisms of the unit object there, so that's just cochains on BG. And on the other hand, when you take global sections of the structure sheaf, all you're getting is you take functions and then take the ones which are invariant. And in fact, this is a well-known statement. This is something you learn in algebraic topology 2 or something, which is just like the cohomology of BG. It's just you take the Weil invariants in functions on, say, the Lie algebra of the vector torus. And then, so this is just a statement of this is like you take sim on P dual, maybe put in degree -2, Weil invariant, And then there's a theorem which says these are also the same. This is kind of a well-known fact, and in some sense, the geometric Satake equivalence is massive generalization. But this is not, I mean, this is a bit of a circular argument. In fact, the isomorphism that I wrote here, it's actually used in proving geometric Satake. So I'll hopefully explain this also a little bit later in the talk. So one of the reasons that this was of interest to me is that Quillen actually had studied this affine Grassmannian from the perspective of homotopy. And what he showed was that using this like Brouhat-Hit theory, he showed that the affine Grassmannian is actually equivalent to an object where hopefully I'll like, a little bit happier with, which is the base loop space of a compact B. And so, of course, the category of sheaves is not a homotopy invariant, but there is a large part of it which is a subcategory generated by the constant sheaves. And so, at least this thing can be sort of understood as somehow related to the base loop space of the group G. And in fact, you can use the Satake equivalence to recover a lot of classical calculations about the base loop space of G. So actually, you can Bott, for example, had a lot of results about the base loop space of G using Morse theory, and many of those statements. Well, for example, you can prove things about the homology of the base loop space of G, and you can deduce these kind of statements by transporting them to a statement on this Langlands dual side and doing some calculation here. And in this way, you can recover a lot of really classical results about the base loop space. Okay, so my goal is to understand what happens if K is replaced by a commutative ring structure. So maybe before I do that, I should ask if there are any questions. Okay. So now we'll get to the combinatorial part. So let's just try to understand what happens when the group G is a torus. Already there, we'll see some really interesting homotopy. So if you want, you could take your torus to be just like GM. But the problem with doing this is that you will end up losing some of the combinatorics that makes Langlands duality very interesting. The problem is that basically the dual of the lattice Z is just Z itself, but the dual of a lattice with where you haven't chosen a basis is some other lattice which cannot canonically be identified with the order. Okay, in any case, when you take your Grassmannian to be a torus, I told you that this T is just the base loop space of T, which is just a bunch of points. It's just a discrete set. It's just a lattice, just pi one of the torus, or if you want, it's homomorphisms from GM to T. Okay, so that's one thing. And the other thing from the previous slide was that we were interested in looking at T of O for T mod T of O. I told you that this guy is just a bunch of points. This guy is just homotopy equivalent to T. And how does T act on this? Well, it just acts trivially. There's no other thing it could do because it's just a bunch of points in this connected group. Okay, so together, these two facts that this Grassmannian is just a bunch of points and this T of O acts trivially tells us that this category is actually quite simple. And so let's investigate. Okay, so you're looking at sheaves under T mod T of O, and K is now it's going to be some any in the spectrum. Okay, so this T gives you the co-character lattice. Remember, that's just homomorphisms GM T or pi 1 T. And then this modding out by T of O is just going to give you, well, a copy of the classifying space of the torus. Okay, so now, depending on what exactly you mean by sheaves, you'll find that this is just a big direct sum of just sheaves on BT indexed by the set X lower star P. Okay, so now there's a question we have to grapple with. What do we mean by the category of sheaves on something like BT? So just thinking about what a sheaf on a classifying space should be, it should just be a K module with some kind of T action. But since we're homotopy theorists, we know that there are many different things we could mean by this phrase. So you could either decide you want to work Borel equivariantly, in which case this category of sheaves on BT is just modules over cochains, but maybe modules satisfying some completeness. And so if you write GQ hat K to mean like the formal spectrum of this cochain, so this is this quill-informal group, then this category of sheaves is just, you just take a bunch of copies of this quill-informal group. So you just take homomorphisms from the co-character lattice of P into GQ hat. So let me remind you that the co-character lattice of P is Homs from T to GM, just as how the co-character lattice is Homs from GM to T, and the character lattice, which is what this guy is Homs from T to GM. And so all I'm saying here is that sheaves on VT is just some number, it's quasi-coherent sheaves on some number of copies of this quill-informal. The number of copies is like the rank of the sheaves. Okay, but there's another thing we could mean by this, is suppose K had some kind of genuine equivariant refinement, complex K theory having genuine equivariant K refinement, then you could mean something slightly different by the category of K equivariant K modules. You could mean something like, K modules in P spectra. And one way to sort of formalize this is giving a genuine equivariant. One way to give a genuine equivariant refinement of your K is to take this quill-informal group and kind of choose a decompletion of it. For example, for elliptic homology, you take an actual spectral elliptic curve, which decompletes the quill-informal group, which is a formal elliptic curve. And all you're declaring now is that instead of some number of copies of GQ hat, you just have some number of copies of GQ. And this could be what you mean in the genuine equivariant. So, in other words, to write down what you mean by this category of sheaves on VT with coefficients in K, well, you have to decide what you want, whether you want to work with the genuine equivariant world or with Borel equivariant. And I'll kind of hide this in the notation. I'll think of it as meaning that I either give more structure in K or I don't. So let me, for notational simplicity,
Wait, I'm sorry,
instead of writing,
Sanath, can you hear me?
yes,
I,
yes.
yeah, I was going to go back over here. So you're describing these things like, like, you know, things that we recognize in about Borel spectra
Yeah.
or genuine spectra, and I just wasn't fully parsing the thing that I should recognize. Could you spell it
So
out?
let's say T was GM, then I'm saying that sheaves on DS1 with coefficients in K. You could think of, well, let me put this. You could think of sheaves on DS1 with coefficients in K as modules over cochains on DS1, but maybe some completeness conditions, which you could think of as quasi-coherent sheaves on this quill-informal group. The quill-informal group is, by definition, split of cochains. Oops, this is cochains on DS1. Sorry.
Oh, I see. This is the So you're saying that this is the almost tautological statement, or
Yes, exactly.
it's the I guess the thing that's happening is like quasi-coherent sheaves can be expressed
Yeah,
as modules.
exactly. Yeah,
But then
everything here is acyclic.
maybe the homotopically non-trivial thing is that a Borel spectrum is encoded in this module.
Yeah, exactly. Yeah, I mean, this equivalence is maybe not so obvious, but it's some Barbeck type of
Right.
identification.
Right. Okay. Okay.
Yeah.
Gotcha.
Okay. So yeah. So instead of trying to distinguish between the Borel and the genuine equivariant case over and over again, let me just introduce this notation. H spec K can mean either the quill-informal group or some decompletion of it, depending on whether I want to work in the Borel or genuine equivariant. So then I'm just going to restate the thing from the previous slide. So we're going to take Homs from this character lattice of T into this H spec. And yeah, so then sheaves on Gert T mod T of O is just some number of copies of quasi-coherent sheaves on this T spec. But I want to point out that like on the one hand you have this I don't know. On the one hand you have this character lattice showing up, and over here you have the co-character lattice showing up. And this sort of is going to be one of the reasons that Langlands duality comes into play. Okay, so what I want is, okay, so now I've gotten somewhat close to proving a theorem of the flavor that I want, that sheaves on something is quasi-coherent sheaves on something else, but I still need to interpret like this funny direct sum in some algebraic geometric way. And so the way I'll do that is I'll just say, let me define an algebraic group over K, so a spectral algebraic group, by declaring I'll define T check of K to be spec of like sort of group algebra on this co-character. So what this means, for example, is that maybe I'll use white. What this means is that if you look at Homs from T check to GM, everything happening over K, then this will actually be the co-character lattice of the torus, which is Homs from GM to T. So this is sort of the crux of Langlands duality in some sense. It's like you replace this combinatorial data, which is Homs from GM into a torus, by Homs from some different group into GM. So in this sense, like T and T check are Langlands dual tori. So maybe you can think of it as like some almost an algebraic version of Pontryagin duality. And the point is that, well, this is an algebraic group, which is a commutative group scheme, and so representations of it are just indexed. The irreducible representations are just indexed by these homomorphisms, and therefore they're indexed by element of X lower bool of T. Okay, but now this tells us exactly how to write this algebra geometrically. Namely, you just tensor this category with Q colon T spec, which is just the same as Q colon T spec times B T check. And so this is the Satake equivalent. So roughly speaking, you had Gur T mod T of O, and here we had T H spec maybe times point mod T check. And what's roughly happening, this is very, very impressionistic, this Gur T piece became the T check, and this T of O bit became the numerator. This equivalence is sort of the Uber equivalence in geometric language. I say this only with some jest. I mean, it's like, it's very simple combinatorics, but really almost everything in geometric Langlands duality comes from understanding this very, very simple case of the torus. Actually, I want to point out that nothing that I said really needed T to be like a connected torus. You could actually just do it for any compact abelian G. In particular, you could take T to be a finite. And then in that case, this T check K thing is just a Pontryagin dual. This Gur T is just a point. And if you unwind what this equivalent is saying, it's literally just HKR character for a finite group. So you could think of the Satake equivalence as maybe some version of HKR character theory for compact abelian groups, which are not necessarily finite. Okay, are there any questions about it? I realize I was maybe going a little quick, but um, it is mostly just combinatorics, just matching up various objects.
I have a question. Um,
Yeah.
Do you have an idea for what this decompleted formal group is when K is NU?
Let's talk about this at the end of the talk.
Okay.
Yeah. Anything else?
Yeah, can you say a little bit more about this interactive theory and what happens to the torsion?
I can't hear.
Sorry, can you say a bit more about HKR character theory and what happens to the torsion?
What happens to the torsion? Sorry, like let's say T is Z mod n. Okay, so then this Gur T thing, I told you it's something like the base loop space, but it's actually just a point. And then I'm just saying you look at sheaves on point mod Z mod n, so it's just sheaves on B Z mod n, coefficients in K. And basically what I'm saying is that this should be the same as quasi-coherent sheaves on what? Well, okay, so this T spec thing is just going to be the n torsion in H. And then you're just going to be multiplying it by n. I mean, the fact that you get the n torsion in H, this is just HKR character theory. I'm just saying that the cohomology of BZ mod n is just n torsion in H. So
But
I'm not saying anything terribly
Hopkins
deep.
character theory, you also have a different type of torsion, but you have this p-powered torsion.
I'm sorry, what?
Hopkins-Ravenel character theory, you have p-powered torsion. Where's the p-power?
Did you hear the question?
I mean, I'm just you could take n to be power of p, and then you will see p power torsion p bar. Um, okay, so okay, I think we succeeded with tori. Maybe others disagree, but I think we've succeeded with tori. And I want, well, given how nice the answer was for torus, namely you literally had just quasi-coherent sheaves on some stack, and sort of the numerator corresponds to the denominator, and the numerator here corresponds to the denominator here. It's very natural to wonder what happens if I replace sort of T by a general group G. So by analogy to H-character theory, this is kind of like asking, instead of doing H-character theory for finite abelian groups, what happens for finite groups? And this was a major part of the HPR paper. Um, and yeah, so we'll try to do it for reduction. Connected. Everything's going to be connected. I'm not ever going to work with finite. Okay, so as with everything in the theory of reductive groups, you first fix the maximal torus, called a Cartan subgroup, although actually it was discovered by Killer. So in this case, you want to make sense of, this category of sheaves on GER G mod G of O, coefficients in K. And so there was a question of, well, what do I mean by sheaves on a stack? Do I mean Borel equivariant or do I mean genuine equivariant? And the Borel equivariant world, this is perfectly well defined. In the genuine equivariant world, this is a work in progress by these two groups of people. I won't need the specifics of like how exactly these category of sheaves are constructed. All I'll need is that they exist and satisfy some basic formal properties. So one can make sense of this category of sheaves on GER G mod G. Now the problem is, what do we do in the Langlands dual scheme? Because you see, the thing that appeared here was we had this TH spec. Everything on this side was a spectral stack over K. And so there are two pieces we need to try to understand. First, what does this fit get modified to? And second, what does this fit get modified to? But we run into a problem with the second group because here this T check is defined over K. But if you remember this geometric Satake equivalence for like the rational numbers, you had something like GK modulo G check K. And so you would need something like this dual group to be defined as a spectral scheme over K itself. So as I said, if you're an ordinary commutative ring, you're replaced by the Langlands dual group defined over K. And what this Langlands dual group is it's so just like how G has a maximal torus T, you can try to build a new reductive group whose maximal torus is not the T that we had, but the T check that we constructed. And this is the definition of the Langlands group. It's it's an algebraic group whose maximal torus is the dual of the original. But if K is some random commutative ring spectrum, you're a bit stuck because you need to make sense of the G check K as a group scheme over K. And that's that's a bit hard. In fact, you might wonder if it's even possible. And sometimes the answer is no. So you actually cannot lift SL2 even to connective KU as an E4 scheme. At least you cannot naturally do so. And the reason is basically that if you are an E4 algebra, then you have some power operations. And SL2 is defined by this relation determinant of AB CD equals 1. So this is AD minus BC. And so you would need that this AD minus BC minus 1, that the ideal generated by this relation is somehow preserved by power operations. It's kind of an easy calculation with like delta structures that this cannot be possible. So you cannot lift it as an E4 scheme, but maybe you can lift as an E3 scheme or as an E2 scheme. I genuinely do not know. I think it would be really cool to construct a lift as an E3 scheme. I think it should be possible in consonance with what the geometric language philosophy suggests, but I don't know how to actually construct it.
So why do you want to lift that action?
Why do I want to lift this thing to K? It's because, so when we were looking at things like with rational coefficients, this Bezer-Klobnikov-Finkelberg equivalence gave us quasi-coherent sheaves on this G over the rational numbers modulo G check over the rational. And if I wanted to replace this Q by something else, maybe I'll use a different color. If I wanted to replace this Q by some other K, then okay, maybe I have to modify the numerator. But I would also have to somehow, find some way of defining this as a spectral stack over K. And what I'm saying here is that I don't even know how to forget about lifting, you know, G check as a group scheme. I don't even know how to lift it as a scheme over K. And so this makes it, I'm not sure a priori what am I supposed to do on this right now. What is the Langlands dual supposed to be over K?
So what was the story with SL2 that you just erased down there? What's this SL2?
What was the story with SL2? Sorry, like if I take G, so I was saying that if I wanted to make sense of VG check over K,
Yeah.
I was just saying let's imagine that SL2 was G check. This is an example of a reductive group, and I'm saying that I don't even know how to lift this to KU. In fact, it's provably not liftable as an E4 scheme, but maybe it lifts in some weaker sense. Like the ring of functions could only be an E3 algebra or an E2 algebra.
So how yeah, okay. Maybe after the talk.
Okay. Okay, so yeah, so let's, so what do we do? I mean, we have this failure where we don't know whether we can lift a reductive group to KU, so we don't know whether we can make sense of this kind of object on the spectral side. But what can we do? Well, one thing we can do is sort of pretend that this thing exists and see what consequences it might tell us about ordinary algebra. So let's pretend that there was some kind of Satake equivalence where we had sheaves with coefficients in K, and this was quasi-coherent sheaves on some like stack. Who knows what the stack is, but this stack should have something to do with G. So for example, if K is Q, then this XK thing should be G over Q, maybe with some shift or something, modulo G check over Q. And this is due to this is the Beznikov-Finkel from the beginning. So we at least have one example of this. We also have another example, which is when G is a torus. And then we know that this XK thing should be this T H spec guy times B T check. Okay. So we have two examples of what this XK thing should be, but what should it be in general? So let's pretend that this coefficient K was even. Then if you had some spectral K stacks or stacks in K algebras, I suppose it was locally constructed from even affine K schemes. But then you can always write down some one parameter degeneration in an ordinary graded stack, which I'll call X part, which is just given by you take the structure sheaf, which is some sheaf of K algebras, and then you just degenerate it to the homotopy this sheaf. So this is some way you can always take some spectral stack, which is locally even, and degenerate it to an ordinary stack. If you want, you could think of it just like even, maybe a sheafy version of it. Okay. So if you had this equivalence, then what you could do is you could imagine trying to degenerate this K to an ordinary stack over pi star. And so you would get some degeneration from sheaves on GER G to just quasi-coherent sheaves on this XK thing, where this again is an ordinary stack. So it's an ordinary stack over pi star K, and this is a K linear category. So in other words, I'm saying you can degenerate this K linear category to a pi star K linear category. That's what you would have if you had this. So let's just forget about trying to construct a K, and let's just try to construct what it could degenerate. And then there's a secondary question. Okay, once you've constructed the degeneration, like, can you lift it to a spectral stack? That's a secondary question. Maybe we don't think about it. So the question, the new goal is try to construct this ordinary pi star K stack and try to actually prove that there is this one parameter degeneration. Instead of like making vague statements, oh, maybe there's an equivalence of some stack we don't know how to construct, let's just actually try to prove that there is a degeneration. Well, then the question is, what should this XK hard thing be? What if there was an equivalence like this? What should the underlying sort of classical stack of this XK be? So I said we have two examples of the stack. One is if K is an ordinary commutative ring, then this work of Bezirkovnikov and Finkelberg tell us that this xk should be just the adjoint quotient stack. You take the Lie algebra of G and you mod out by this G cap. And again, everything is living over pi star k, but in this case, pi star k is just k. On the other hand, we also know what happens when G is a torus and k is an arbitrary E infinity ring. In this case, this xk guy is just you take this th spec from before. So remember, this was a thing built from some number of copies of the Quillen formula group or some decompletion thereof, times this bt check. So if we write H to be the underlying stack of either the Quillen formula group or this decompletion of it, then I'm just saying that you just have the ordinary stack is just th times bt check, where th is just some number of copies of my ordinary group scheme H, and t check is just the ordinary group scheme given by the Langlands rule of torus. So I just want to emphasize that everything here lives over pi star. There's no spectral algebraic geometry. Okay, so does the goal make sense? Like, instead of trying to construct some spectral stack, which, who knows how to do that, I'm just saying, let's just try to construct the ordinary classical stack, which it degenerates to, and see what, well, let's just see what that stack should be. Maybe we can then try to lift it to spectral stack. I won't do that. Are there any questions?
So just
Okay.
just so I fully understand,
Yes.
in the case of, are you saying that in the case of, in the case of H being, or K being, like, say, an elliptic cohomology theory, are you saying
Yes.
that, and say the torus is the boring one, the GM, are you saying that the
Yes.
H
Yeah. So
is
then
the
this guy,
associated elliptic curve?
yeah. So either it's in the Borel case, it's just the completion of the elliptic curve,
Yeah.
or the identity, or it's T itself. That's right. Exactly. If T is GM. That's right. So yeah, okay, again I made a typo. So note, so this H, I told you it's this degeneration, and so for example in the Borel case, it's just flip of the cohomology, like it's cohomology, not cochain, cohomology of BS1. Okay, so what will we do? We will write this xk part as a quotient stack. So so remember in the previous slide we said this xk for the ordinary commutative ring was like some Lie algebra thing modulo the group. And basically, the intuition that you should have at this point is that for an ordinary commutative ring, this H, depending on whether you want to work Borel or genuine experience, it's either GA hat or GA. So in some sense, it's linear, and that's kind of why you're seeing the Lie algebra show up. Okay, so you see this show up because it's linear. And what we're going to now try to do is we're going to say that for a general cohomology theory, xk part should be some kind of quotient stack, GH mod G check, and this GH should be some kind of nonlinear deformation of G, which depends on H in some way. So for example, when you plug in the additive group, maybe with coordinate in weight 2, you'll just get the Lie algebra. This is the example from the first example from the previous slide. And also, if you plug in G to be a torus, then for any H, you'll just get Toms from this co-character lattice, from the character lattice bit. Okay, so yeah, and what this notation means is I just do the Langlands rule group. It's defined over Z, and I just pull it back to Python. Okay, so a bunch of people have converged on a definition that would give you what this GH thing is. So Fertilla, Gunningham, and Lee, they came at it through some ideas in elliptic Springer theory. Molinos, Raballo, and Towen came about it through like trying to write down HKR filtration geometrically. Adil Khan and Bouaziz came up with it also through some ideas to geometric representation theory. I came about it when writing up my thesis, and the definition is very, very simple. Basically, for any scheme or any stack, I'm going to write down some version of the loop space, the free loop space of this stack. let's say I start off with a stack over pi star k. I can then define the free loop space of H, the H loop space. And I'll define it sort of using the Tanakian form. I'll say it's sort of tensor colimit preserving functors and quasi-coherent sheaves to end of the category of coherent sheaves of length 0. And I have to equip this with some monoidal structure, and the monoidal structure is given by convolution. So if I take two coherent sheaves of length 0 and H, then there's this product map, and I just push forward. So that's because H is a commutative group. This is actually a symmetric monoidal structure. Okay, so this picture simplifies quite a lot if H is a formal group. So for example, if it's a formal group, then it's just maps. It's just a mapping stack where H check is the Cartier dual of H. So it's just maps from BH check to X. Okay, that's just because you can identify this as something like quasi-coherent sheaves on BH check. And it was in this sense that it was discovered by Molina Trabalo. They had this definition of the H loop space. It doesn't work if H is an elliptic curve because, for example, the Cartier dual of an elliptic curve is 0. But if you work with sort of this kind of definition, then you will get correct H loop space.
It's not
yeah.
Does this version have anything to do with like the usual loop space, like the derived intersection of?
Yeah. So maybe I was gonna. I don't know if I had this example. So yeah, let's say H is GM. Then this H loop space of X is just maps from the circle to X. So it's the usual thing.
Gotcha. Okay.
Maybe I'll give another example. If H is GA, then this H loop space of X is just you take the tangent bundle of X and you shift it by -1. So the way Molina, Trabalo, and Toen thought about this was that GM has a canonical degeneration of GA, and at the level of these loop spaces, that gives you a degeneration from the free loop space to the tangent bundle. And then that degeneration is the HPR filtration. So this H loop space captures quite a lot of interesting. Okay, so when your X is BG, maybe I'll just forget writing this pi star. Just think of it as like BG. Then there's always a map from the free loop space of BG back to BG. And well, there's also a map from, well, like back on a point, back on pi star k, and you can consider this pullback. And this pullback is what I'll call GH. Okay, so for example, for the multiplicative group, this LH, the BG, is just G mod G acting by conjugation. And so when you map to BG and you pull back to a point, you're just going to get the group G itself. So for example, this is what G sub GM. Okay. So here's a bunch of examples. I just gave you some. So here's a table. So H is, for example, GA. Maybe you put the coordinate in weight 2, then you'll just get the Lie algebra. And this basically comes from the fact that I said earlier, H loop space and it's something like the tangent bundle. Maybe with some shift. In this case, so LGA. But you can also take GA hat, and then you won't get the Lie algebra, but you'll get the Lie algebra completed at the cone of nilpotent elements. So this is the cone of nilpotent elements. Take GM, you'll get the group itself, as I explained. If you take GM hat, you'll get the group completed the unipotent elements. For an elliptic curve, you'll get the moduli space of semi-stable G bundles on the elliptic curve with the trivialization of the space. So, E, there's a map in from a point, and you have some G bundle, and you can ask for a trivialization. This is just some G module, you can ask for trivialization. Yeah, as I said, this N is the cone of nilpotent elements, and U is the cone of unipotent. So whether you work with GA or GA hat or GM hat just amounts to whether you're doing completion in nilpotent or unipotent.
Could you say again what you mean by the triv in Bun SSG?
Yeah, so if I have an elliptic curve over some base S, then there's a 0 section. And if I have a G bundle, then I can pull it back to the 0 section. And now this is a G bundle over S, and I can ask for a trivialization.
I see.
That's what I mean. So for example, there's a G action on this guy, which just comes from changing this trivialization at 0. Okay, so now I can finally get to the conjecture. So I'll use this GH to write down a conjecture about what should happen under Langlands duality. So let's say K is even, and G is simply laced and simply connected. So this just means, again, SLN from spin 2N, P6, P7, or P8. But if you want to just think of SLN. So then the conjecture is that there's this one parameter degeneration. So like there's a filtered category whose underlying category is this category of sheaves, and his associated graded category is quasi-coherent sheaves on this quotient stack. So you take GH and you mod out by G. And again, this side is K-linear, but this degeneration implements taking homotopy groups. So it's sort of like pi star K-linear category. You should think of this as some sheafy version of the even filtration. Like, well, I'll hopefully explain this in the time that I have. Roughly speaking, the even filtration is like you take modules over the infinity ring, and you can sort of generate to get quasi-coherent sheaves on stack, even stack. And this picture is sort of saying like we can non-linearize this category by looking at not just modules but sheaves of modules, and then those should also have some interesting things. And this is a particularly interesting example of that. Okay, and if K is not even, just work even locally. If you want to do it with the sphere, just work with mu and then descend. Maybe I will skip this. Okay, yeah, I'll skip this. Okay, so let's see what the conjecture says, this conjecture, when K is an ordinary commutative ring and also when K is a sphere spectrum. So if K is an ordinary commutative ring, the conjecture says what? In the genuine equivariant setting, it says if you take sheaves on G mod G of O, then you'll get quasi-coherent sheaves on, this is my GH, remember? You'll get quasi-coherent sheaves on G, the algebra of G mod G check. And this is essentially the Bezdrakov-Finkel from before. So, okay. In a Borel equivariant setting, then instead of this G, you'll get sort of a completion at the nilpotent cone. And this is what people in the geometric Langlands literature call like the renormalized version. Okay, but whatever. I just wanted to explain that sort of this thing which the representation theorists think of as being kind of strange actually just has to do with Borel versus genuine equivariant. Okay, so on the other extreme, instead of K being an ordinary commutative ring, let's take K to be the sphere, but now let's take G to be the trivial. If you work even locally, then you'll find exactly this degeneration. Sheaves on a point, which is just the category spectra, two quasi-coherent sheaves on the moduli form. Okay, now, okay, in, perf, Fuco, whatever. It's just quasi-coherent sheaves. So one could sort of think of the conjecture from the previous pages from mixing Langlands duality, just mixing the interesting geometry of the affine Grassmannian with the interesting homotopy theory, like the sphere spectrum. So you mix Langlands duality with Adams-Novikov. And that's exactly sort of like you have this funny stack GH mod G check, and it kind of lives over MFG if H is the universal formula. And so it sort of varies in a very interesting way as your H varies. And that variation is somehow I don't know, it's somehow very interesting, and somehow it's captured exactly by the topology of this affine, according to the conjecture. Okay, so what uses the conjecture without evidence? Okay, I guess there are two pieces of evidence, but here's a bit more substantial evidence. It's not quite correct as written, but basically here's the theorem. Suppose you take K to be the integers, or KU, or capital KU, you know, connective KO, or capital KO, or J, or elliptic homology. And let's also suppose G is not a type. Apologize, it's a bit of a weird assumption. It comes from the fact that E8 has no minuscule weight. Then the statement is that there's a filtered category over the even filtration of K, such that the underlying category is sheaves on GER G mod G equal, and the corresponding associated graded category, so that lives over GER star E, and that's equivalent to quasi-coherent sheaves on GH mod G. Except I don't know how to prove this on the nose. I can prove it upon base change for an algebraic decomposition. This is kind of like how in HKR character theory, like for a non-abelian group, you really have to, extend scalars from Morava E theory to this funny CP ring, C0 ring, and this is kind of similar to that. I don't think it should strictly be necessary when G is a connected reductive group, but I only know how to prove it upon base change for another. So, in other words, what am I saying? I'm saying that the conjecture from the previous slide, that this guy degenerates to this, is true as long as on the degenerated side you base change for an algebraic approach field. In fact, when your group is GLN, you don't need to do this base change. Maybe I'll mention that in the particular case when K is periodic K theory, this kind of idea, well, not the degeneration, but kind of trying to prove some equivalence between this and, well, so what is it when K is KU? So then this GH mod G check is G mod G check in this case. And in this case, trying to understand this category in terms of the stack was previously proposed by Crowder and Chandler. But they have a very different proof of this, where they write down an explicit combinatorial model for both sides and check that the combinatorial models are the same. This is not quite how the proof, well, this is not how the proof of this theorem, but, well, maybe I'll just say it. The main tools in this theorem are you have to compute equivariant homology. And this is where you have to generalize work of Bott. So like when K is an ordinary commutative ring, you're just looking at the equivariant homology, where G acts on loops G by conjugation. And you have to describe this in terms of the dual group G check. And you also have to use some kind of purity argument, where you have to somehow use that GER G. It's kind of like a flag variety, so it has like a decomposition into affine spaces, and it's unstably cellular, and you have to somehow use that to prove this theorem. This cellularity is called the Schubert filtration. So, okay, maybe. Oh yeah, okay. So maybe let me make a brief remark about this. I have a lot more slides, but I'll only get through maybe two more. So there's a degeneration. Okay, forget about this NH thing. If you want, just think of it as GH. So how are you supposed to think about this? Like, what should a homotopy theorist think when they see this? Okay, I'm not working with a non-equivariant person. That didn't talk. Okay, so what should a homotopy theorist think? So remember, when G was 0 and K was a sphere spectrum, this side was the category of spectra, and this side was something like quasi-coherent sheaves in the moduli of forming main perf, whatever. And one way to think about this is through the world of synthetic spectra. One way to implement this degeneration is through synthetic spectra. But you can also profinitely complete and instead think about the category of cellular motives over the complex. Okay, so this suggests some interesting relationships between geometry and homotopy. So for example, let's say I have some X which is a scheme, and let's say it has a cellular stratification. Each stratum is an affine space. What you can then do is form the category of motivic spectra on X, where you ask that the star and streak restriction to each stratum. So each stratum is just an affine space, and you can ask that the star and streak restrictions are cellular. This is cellular in the usual sense of the word. They're generated by the Tate twists. So then, upon profinite completion, okay, this category of sheaves with this parameter tau that we all love inverted, it's basically some kind of profinite version of sheaves of spectra on X, which maybe satisfy some constructibility conditions and some purity conditions. And well, this category, the tau inverted guy, degenerates to tau equals 0. And sometimes this tau equals 0 category is quasi-coherent sheaves on algebraic. So when x is a point, this is literally Q co on MFG or infer. And one way to think about this for general X is that it's some kind of relative version of the theory of synthetic spectra. It's like a version of synthetic spectra which is relative to this base X. And so somehow the geometry of X interacts in a really interesting way with the atom. So roughly speaking, this is not true, I think, on the nose, but kind of close. This degeneration here can be thought of as the case when X is the affine Grassmannian with the Schubert stratification. So roughly speaking, this category is something like motivic sheaves with tau inverted. And this category here, the GH version of it, is something like SH with tau equals 0. You could think of this as some version of synthetic spectra, just done relative to the affine. Okay, so that's maybe remark 1. This whole picture can be thought of as a relative version of spectra. Remark 2 is that, well, one thing you'll often see when you read papers about Langlands duality is it's always thought to be of a motivic nature. So what this roughly means is that whatever happens on the spectral side, anything to do with the dual, is often, in some sense, ambivalent to the fixed. So, for example, in number theory, when people study like say representations of p-adic groups, they often consider representations of p-adic groups on like QL vector spaces where L is different from D. And they try to write down some spectral decomposition of this category. And somehow all of their conjectures are of the form, you have something which looks like it should depend on L, but really there's some independence of L involved, which is some kind of statement about, some motivic statement. It's sort of saying that it's really about the geometry and not about the property. So if K is a ring spectrum, then what the conjecture from the previous slide says is that the spectral side, again, that means things that have to do with the Langlands dual group. That this side depends only on the choice of K through the formal group that controls the theory of Chern classes. So it's not that the spectral side, this thing to do with the Langlands group, is kind of ambivalent to K. It's just the only way it depends on K is through the formal group that corresponds to it. So what am I saying? Like, you have the stack GH mod G tech, and this numerator GH, it depends on this formal group H. So as you view it as living over MFG, the fibers of the stack living over MFG, they vary as the formal group varies in MFG. But the denominator, which is a G check, is somehow completely independent. It seems to persist no matter what my cohomology theory is. It's not like the Langlands dual group changes. In fact, it's pulled back along the map from MFG to BGM, classifying the Lie algebra, like the dual of the Lie algebra. So in this sense, it's kind of defined over F1. Like, so in homotopy theory, things which are pulled back from MFG to BGM feel like they should be defined over F1. And so, in some sense, the picture is both. It sort of suggests a slight extension of the motivic nature of Langlands duality, but it's also compatible in the sense that the dual group G check is somehow combinatorial. It's somehow defined over F1, but the numerator depends in some interesting way on the formal H. Okay, I have 1 minute, so let me just skip a whole bunch of stuff. Oh, shoot. Okay. I just want to get to the last library, I think. Yeah, okay. So, sort of, I think that there's a very interesting, algebras and things like this that you can construct by pretending that Langlands duality works for generalized coefficients, trying to see what the geometry says when you make it interact in some interesting way with your cohomology theory. And well, I think that there's a lot that homotopy theorists can say about representation theory. And I'm out of time, so I'll stop there. Thank you.
questions?
Yeah. Sanath, in the
Yeah.
equivariant cohomology computation that you have mentioned, the K that you had like examples of, some of them were like didn't have any complex orientation, like you mentioned KO, I think.
Yeah.
But still, and it,
Well, yeah. So that's what I meant by working even locally. So
okay.
instead of working with like the KO homology or whatever of the Grossmanian, you just work with KU homology and keep track of like complex orientation. Keep track of complex conjugation.
And maybe one more thing, you didn't like. You also mentioned integers. I've seen like there is always some characteristic that you need to invert when you want to calculate.
Oh yeah, sorry, I forgot to mention that. I don't know how to get that. Okay. Yeah, sorry, I forgot to write. Here, the algebraically closed field maybe has to not be. Well, let's say that the algebraically closed field is at least has characteristic at least 31. I think it should be fine.
So
31 because well,
is it like the
2
while
times
loop
3
should
times
complete
5
it?
plus 1. What's up?
So no, I was asking, is it like these like the bad primes that one talks about?
Yeah. 31 is like 2, 3, and 5 are torsion primes for EA, and that's like kind of the worst case situation. So you just work larger than their product, and then you should be fine.
Any questions? Yes?
Ask the same question about the decompleted formal group review.
Yeah. So I think what. Okay. So one thing that you will notice, if I can get to it. Okay. Right. So here's this H loop space guy. Maybe one thing to notice is that this depends in a very minimal way on the group structure on H. Like the only thing you really needed to know was that this category of coherent sheaves of length 0 had some kind of convolution structure. So, where does this map come from? If I think of this H as something like the genuine S1 guy, then this comes from the map AS1 times S1. Well, really, there's a map like this, which, if you have a Kunith formula, identifies with KS1 times. But this Kunith thing doesn't work for NU. So you don't have a map to here. You'll just have a map to here. And I think using this, you can write down some variant of this category, even if H is just one of these like global group laws, for which you can make sense of the H group space. Once you've made sense of that, then the conjecture in the exact same way.
Questions?
Yeah, can you go back to the thing with the power operations and the SL2Z invariants?
Yes.
So what are you trying to accomplish there? So where did the power operations come from?
Wait, sorry, just 1 second. I'm being slow. Okay, there. Okay, so what did power operations accomplish? What they accomplished was the following. Well, if you want to lift SL2, so the G check is going to be SL2. This SL2 over K is going to be some like spec of some ring. And this ring is maybe going to look like over KU, it'll look like K adjoin A, B, C, D modulo AD minus BC minus 1. Now, what I mean by naturally here is that this piece, before you do any modding out, this has a natural lift. KU as like an E infinity scheme. Just adjoin a bunch of flat polynomial generators.
So when you say join those, I'm sorry to interrupt. When you say join those polynomial generators, are you doing it like making the free E infinity KU algebra?
No, the flat guy. So this is like K adjoin like Z greater than or equal to 0 like to the fore.
Okay, so it's like the it's like the free E1 algebra.
Sure,
Yeah.
except not sure. I mean, not literally, right? Because these guys commute. A and B commute.
Okay. Sorry to
Yeah.
interrupt.
This is probably before copies.
No, no worries. Yeah.
Okay.
Huh?
Okay.
Okay. Right. So then there's this ideal that you want to quotient out by, and you want to know like if SL2 had a lift as an E4 scheme, then you would have a delta lift. Then when you take pi naught of this and work mod p squared, so then you will like say B is going A B C D mod AD minus BC minus 1 and p squared, then you'd have a delta. You'd have a delta lift on this guy. And that comes from the structure of E4 KU algebras. And what you check is that this relation cannot possibly, delta of this relation cannot possibly lie in the ideal generated by that relation. So that means that you cannot possibly have an E4 structure on this algebra which is compatible with this, with the natural map into affine 4 space. And that's kind of that's what I mean by this. One cannot naturally lift SL2 to KU. That means that this G-check guy cannot be lifted to KU like as an E infinity scheme or even as an E4 scheme in general. Did that answer the question?
Yes.
Okay.
Alrighty. Shall we thank Sanath